Lesson: Dimensionality Reduction Techniques. Dimensionality reduction techniques are pivotal in the realm of machine learning, providing robust solutions to manage high-dimensional datasets effectively. These techniques are essential for simplifying models, enhancing computation efficiency, and improving the performance of machine learning algorithms. By reducing the number of random variables under consideration, dimensionality reduction aids in mitigating the curse of dimensionality, which can severely affect the performance of machine learning models due to the exponential increase in volume associated with adding extra dimensions. This lesson delves into the practicalities of dimensionality reduction, illustrating how these techniques can be seamlessly integrated into real-world applications, thereby enhancing a professional's ability to implement AI solutions effectively. One fundamental approach to dimensionality reduction is principal component analysis. PCA is a statistical method that transforms the data into a new coordinate system, where the greatest variance by any projection of the data comes to lie on the first coordinate, the second greatest variance on the second coordinate, and so on. This is particularly useful in scenarios where it is crucial to visualize the data or to reduce noise. For instance, in a case study involving facial recognition, PCA can be used to reduce the dimensionality of image data, which often contains thousands of pixels, to a manageable number of principal components that retain the essential features of the faces. This reduction not only speeds up the processing time, but also improves the accuracy of the recognition model by focusing on the most significant features. Another technique is linear discriminant analysis, which, unlike PCA, is a supervised method. LDA aims to find a linear combination of features that characterizes or separates two or more classes. It is especially effective when the goal is to reduce the dimensionality of data while preserving as much of the class discriminatory information as possible. For example, in a real-world application involving customer segmentation, LDA can be employed to reduce the feature space while ensuring that the variance between different customer segments is maximized, aiding in developing targeted marketing strategies. Beyond these classical methods, modern techniques such as T-distributed stochastic neighbor embedding have gained popularity, particularly for visualization purposes. TSNE is a nonlinear dimensionality reduction technique well suited for embedding high-dimensional data into a space of 2 or 3 dimensions, which can then be visualized in a scatterplot. It is particularly effective in revealing the inherent structure of complex datasets, making it an ideal choice for visualizing clusters in a dataset. In practice, TSNE has been used extensively in bioinformatics to visualize high-dimensional RNA sequencing data, allowing researchers to discern patterns and clusters that may correspond to different cell types or states. In addition to these, autoencoders, a form of neural network, offer a powerful tool for dimensionality reduction in an unsupervised learning context. Autoencoders work by compressing the input data into a lower dimensional representation and then reconstructing the output from this compressed data. They are particularly useful in situations where the data is nonlinear and complex, as they can learn intricate patterns and relationships within the data. For instance, autoencoders have been effectively used in anomaly detection tasks, where they learn the normal patterns of data and are then able to identify deviations that may indicate anomalies. The practical implementation of these techniques involves several steps. Firstly, data pre-processing is crucial. This often includes normalizing the data, which ensures that each feature contributes equally to the distance calculations, crucial for the performance of PCA and LDA. Once the data is pre-processed, selecting the appropriate dimensionality reduction technique is essential. This choice depends on the data characteristics and the specific requirements of the task at hand. For instance, if the primary goal is to reduce noise and enhance computational efficiency in a high-dimensional dataset, PCA might be the appropriate choice. Conversely, if the task involves classification, LDA might be more suitable. Once the technique is selected, the next step is to determine the number of dimensions to reduce the data to. This is often guided by the cumulative explained variance in PCA or the classification error in LDA. In PCA, for instance, A common practice is to retain enough principal components to account for at least 95% of the variance, which usually results in a substantial reduction in dimensionality without significant loss of information. Finally, after applying the dimensionality reduction technique, it is crucial to evaluate its impact on the performance of the machine learning model. This involves comparing the model's performance before and after dimensionality reduction to ensure that the reduction has not adversely affected the model's accuracy or ability to generalize. In many cases, dimensionality reduction not only speeds up the computation, but also improves the model's performance by eliminating noise and irrelevant features. The use of dimensionality reduction techniques is not without challenges. One common issue is the potential loss of information, which can occur if the dimensionality is reduced too much. This can lead to models that do not perform well on unseen data. Therefore, it is essential to balance the trade-off between dimensionality reduction and information retention. Moreover, some techniques, like TSNE, can be computationally intensive, making them unsuitable for very large datasets without appropriate computational resources. Statistically, the effectiveness of dimensionality reduction techniques has been demonstrated in various studies. For instance, a study involving high-dimensional genomic data found that using PCA for dimensionality reduction resulted in a significant improvement in the accuracy of predictive models, with a reduction in error rates by up to 20%. Such statistics underscore the potential benefits of these techniques in real-world applications, making them indispensable tools for AI professionals.